Hello everyone. I will talk about a short paper I published recently called Symmetry Transformations of Subregion Representations. This is about how boundary representations of bulk fields transform under symmetries of the boundary conform field theory, and I will explain all these terms as we go. Here is the archive number for the paper. So let me start by quickly recalling the ADS CFT correspondence. In this cartoon, the interior of the cylinder represents an anti de Sitter space of the bulk, and the conformal field theory dual to it lives on the boundary of the space, which is flat. There is a duality between the physics in anti de Sitter space and the conformal field theory in the boundary, and one manifestation of it is that there's a one-to-one correspondence between the symmetries of the bulk, the isometries of the bulk metric, and the symmetries of the boundary theory. So here I have denoted the coordinates on the bulk as r comma y, where r is the radial coordinate and y labels all the other coordinates. So the coordinates on the boundary are just y. And there's a one-to-one correspondence between coordinate transformations in the bulk that do not change the metric, and on the other hand, the coordinate transformation in the boundary, which is symmetries of the conformal field theory in the boundary. Now, the correspondence between ADS and CFT says that the string theory in the bulk is dual to a conformal field theory on the boundary. However, we do not yet know the full dictionary between the two theories. We know some of the entries of the two theories. They are expected to be completely equivalent, and there should be a way to translate from one to the other, but the full dictionary is not quite known. We have some relationships, but by no means all of them. So one of the relationships, one of the entries to the dictionary that we do have is called the extrapolate dictionary. This relates a field in the bulk to an operator in the boundary, which is called its dual. So if phi is a scalar field in the bulk with some mass m, it will be dual to a scalar primary operator O in the CFT with conformal dimension delta, where the mass of the scalar field and the conformal dimension delta are related by this equation here. The duality relation tells us that if I compute the correlation function of the bulk field using the bulk field theory and take this particular boundary limit, then what I will obtain is a correlation function of the dual CFT operator. So this gives us a way to map the boundary behavior of the correlation function in the bulk field to an object in the boundary theory. However, to translate completely between bulk physics and boundary physics, we need to go beyond this. This is telling us how the boundary behavior of the correlation function, boundary behavior of the bulk fields. What we would like is to completely describe the bulk field, completely translate the bulk field to something, some object in the boundary theory. And this brings us to the bulk reconstruction program, which was contributed to by people whose names appear here. So the idea is to translate between bulk and boundary physics by completely translating bulk fields into boundary operators. So what does this mean? So the aim here is to construct operators in the boundary theory that are doppelgangers of the fields in the bulk, operators which will mimic bulk fields. So for a bulk point Ry, we want to construct an operator in the boundary theory that mimics the bulk field phi, and we call this boundary operator phi CFT. And I have put Ry in brackets, which may be a bit confusing because this is a boundary operator and Ry are bulk coordinates. What this means is that this boundary operator mimics the bulk field at r comma y. So we define phi CFT by the demand in the boxed equation here. This says that the correlation functions of this operator phi CFT calculated in the boundary field theory should be the same as the correlation functions of the bulk field calculated from the bulk field theory. If this is so, phi CFT will capture all the information about the bulk field. Now, when the bulk scalar is a free field theory, phi CFT takes the form as shown here. So let's unpack this equation here. First of all, we see in the right hand side, there's an integration over, I have written boundary region. So there will be an integration over some boundary region, which I will specify shortly. And the integration is over the primary operators, which are dual to this scalar field phi. So phi CFT is a boundary operator not at some particular boundary point, but it is integrated over some region. It is a non-local operator. And in this integration, the boundary operators are weighed by this function k, which is a function of both the bulk point r comma y and boundary points y prime. And this is called the smearing function. The smearing function is what carries information about the bulk point. Now there are at least two inequivalent constructions of the boundary representation phi CFT. The first is what might be called the global representation. Here for a field phi anywhere in the bulk, one can find a CFT representation, and that will have the same form that we just saw. And the boundary region of this integration will be over the entire boundary. Actually, this isn't quite true. It can be made smaller, but that's not relevant for our purposes. So here in this picture, we show this is the bulk, and in the left hand side, this is the bulk, and this is the boundary, which we have unwrapped. And then the integration, when we try to construct a operator for a bulk field phi somewhere in the bulk, it will have this form that we saw, and the integration will be over the entire boundary. But there is another inequivalent construction called the ADS-Rindler construction, and this is named after a coordinate region in the ADS called the ADS-Rindler wedge, which is shown in this picture. ADS-Rindler wedge is shown in blue. It is a region that does not cover the entire ADS space, and so the boundary of the ADS-Rindler region looks like this blue diamond in the picture here. Now for a point anywhere in the ADS-Rindler wedge, we can obtain a representation again of this above form and this however, in this case, this boundary region of the integration will not be the entire boundary, but only the boundary of the ADS-Rindler wedge. The picture here is of the original ADS-Rindler wedge, but one can obtain such boundary representations for any coordinate region which is isometric to the ADS-Rindler wedge. And by abuse of notation, I will call all such wedges as ADS-Rindler wedges. So this was the introduction to bulk reconstruction. Now we come to the concerns of this paper about symmetries. As we said in the beginning, there's a one-to-one correspondence between bulk symmetries and symmetries of the boundary. So the bulk theory will have killing vectors that impose the symmetries, and this will be dual in the boundary theory to generate it. There will be one-to-one correspondence in the boundary theory to symmetry generators that act on the boundary Hilbert space. The J mu here are the symmetry generators of the boundary theory, and they are in one-to-one correspondence with all the killing vectors in the bulk. Now the question here is, how does the boundary operator phi CFT transform under the symmetries of the boundary CFT? This is a boundary operator, so this should have some kind of transformation under the conformal symmetries of the boundary CFT. We know how the bulk field, it mimics transforms under the bulk isometries. it goes like this. So how does the boundary operator transform? The case of the global boundary representation, the first case that we saw, was considered by Ugui and Nakayama, and the correct answer, as shown by them, is this equation. This is telling us that phi CFT transforms under boundary symmetry as if it is the bulk field transforming under the corresponding bulk isometry. So there's a beautiful consistency between the boundary symmetries and bulk isometries. In the language of finite transformations, if a bulk isometry maps a point x to x prime, then phi CFT transforms under the unitary implementing the boundary symmetry that corresponds to that bulk isometry. Now we can ask the same question about ADS cylinder representations. How do they transform under symmetries? And that is the question that we have asked in this paper. The complication for ADS cylinder is that a generic bulk isometry will not leave the ADS cylinder coordinate region invariant, but map it to a different ADS cylinder wedge. So in this picture, we see a simple case where the isometry is just, we can take it to be a rotation, and so this wedge A is mapped to a different wedge B. But the boundary representation for A, let me give the name phi CFT A for the ADS cylinder representation in A, and similarly phi CFT B here. So let's talk about phi CFT A. So phi CFT A is an operator integrated over the boundary of A, which we have shown here. So this will be integrated over this region here. But under the isometry, this region is not. Under the conformal transformation corresponding to the bulk isometry, this region is not preserved. It is mapped to this region here. So it follows that this relation that I've written here, which is the exact analog of this equation, for phi A CFT cannot be true, because this unitary operator which implements this symmetry will take a point in the from boundary part of the wedge A to the boundary part of the wedge B. So this relation cannot be true because this integration region has now changed. But notice that as an isometry maps one ADS cylinder wedge to another, it's the corresponding boundary symmetry maps their boundaries together. So the unitary map U lambda will map an operator at some point y here to some point y prime here. So this means that the operator phi A, when we act on it with this unitary, so operator phi A was integrated here, it will be mapped to some operator which is integrated in this region, the boundary part of the wedge B. So we are led to suspect that maybe it is mapped to the boundary representation phi B of CFT, the boundary representation corresponding to the wedge B. And we conjecture that this relation holds. This says that the unitary map implementing the boundary symmetry, although it does not preserve the wedge, it can map one ADS cylinder wedge representation to a different ADS cylinder representation. And in this paper, we proved that this is indeed true. A similar calculation as that proof had been done in a different context in this nice paper by Kim. So to summarize, we asked how ADS-cylinder representations of bulk fields transform under the symmetries of the boundary theory, and we found that the boundary symmetries will map one ADS-cylinder representation to another. And so this equation is the final result that we obtain. Thanks a lot for listening.